In this video, we're going to look at how rocks and other minerals can be dated using uranium-238 and lead-206. So the idea behind this dating technique is we have rocks that initially contain some amount of uranium. And because uranium is radioactive, over time, that uranium decays. And this is a multi-step decay series, but because uranium-238 has by far the longest half-life, that's what we can use for dating the rock. And so the end of that decay series is lead, and it's specifically lead-206. And so over time, the amount of uranium decreases and the amount of lead increases. So the more lead there is, the older the rock is. Now, each uranium atom changes into a lead atom. But of course, we know that the mass of a lead atom is less than the mass of uranium-238. So when we're finding out the initial amount of uranium, which is going to be our N0, we have to take that into account. And so we can use the ratios of the masses here that for every 206 grams of lead, I would have 238 grams of uranium. And so this is essentially a conversion factor that we're going to use when solving this problem. All right, so this is what a sample problem might look like. So we've got some mineral. Today, it contains 75 milligrams of uranium and 18 milligrams of lead. And so in order for this dating technique to work, the sample can't have any lead in it when it was formed. And then we're given the half-life of uranium-238. So the first thing we need to do is figure out, if I want to know how old the rock is, I'm looking for T. So I need to know NT, N0, and K. So K we can find the way we've done in all our other examples. And the NT we know, right? So the NT is the 75 milligrams of uranium-238. What we need to find is N0. And so I like to think about it with a little diagram. All right, so I've got originally when the rock was formed, and then I've got the rock today. All right, so now we know today that I have 75 milligrams of uranium and 18 milligrams of lead. And so the amount of uranium that's left, this is my NT, right? And that 75 milligrams that I have today, of course, right, that would of course existed in the original rock, right? And so what I need to figure out is this 18 milligrams of lead, right, it makes up this part of my N0, and so I need to figure out how much did that lead weigh when it was uranium, right? And this whole thing is my N0. So the conversion factor we had from the last slide was that 206 grams of lead would be equivalent to 238 grams of uranium. Now in this problem we're using milligrams, so in my conversion factor it'll be 206 milligrams of lead is equivalent to 238 milligrams of uranium. So I can take my 18 grams of lead, right, in order to get the units to cancel, I'll put my 206, sorry, this is milligrams. I'll put my 206 milligrams of lead on the bottom. So then 238 milligrams of uranium will go on top. And when I multiply that out, I get 20.8 milligrams of uranium. So that's what this piece was, 20.8 milligrams. So then I know N0 is going to be 75 plus 20.8, or 95.8 milligrams. All right, now the rest of the problem is going to be exactly like all the other examples we've been doing. And so it's just this part that's unique to the uranium and lead dating. All right, so we'll finish it off on the last two slides. Okay, so I've collected what we know so far. We found the N0 on the last slide. We were given NT, so I need to find K, so we'll do that on this slide. So K And now for the half-life, I could either write 4.5 billion. That would be 4.5 times 10 to the 9th years. So I could either use this for the half-life, in which case my units would be years, or I can use 4.5 as my half-life, and then my units are going to be billions of years. So I think working with 4.5 is going to be easier than working with 4.5 times 10 to the 9th, so I'm going to do that, and then my units will just be billions of years. All right, so when I divide that out, I get K is 0.154, and that'll be 1 over a billion years. And then we'll plug all this into here on the next slide to finish the problem. All right, so I've collected everything we know so far. I've got my N0, we've got my NT, here's the K we found on the last slide. And so now I can say, all right, NT N0, e to the minus k, and t is what we're solving for. So divide both sides by 95.8. And I get 0.783 e to the minus 0.154 t. Take the natural log of both sides. So I get negative 0.245. L and the e cancel, so the exponent comes down. All right, we'll finish it off. And so I get t to be 1.65. And because we used the half-life in billions of years, the k was 1 over a billion years. And so then the time will again be billions of years. So this mineral sample is 1.65 billion years old.